Hello and welcome. In this video, we're going to be talking about uniform circular motion. So let's go on and jump right on into it. So uniform circular motion. First off, as always, let's define what it is that we're talking about. So when we look at kinematics, kinematics says that any object that moves in a circle at a constant speed is said to experience uniform circular motion. So let's take a look at that. I've got a stopper connected to a string. And if I take this and I start twirling it, okay, as it's moving, first and foremost, it's moving in a circular fashion. Secondly, its velocity is constant. So this would be considered uniform. So it doesn't matter that I've got this in the vertical component, that in essence it's moving up, over, and then back down within that vertical plane. I could just as easily take this and put it into horizontal circular motion, where now it's moving along that horizontal plane. I could even take this and set it at some angle. It's still moving in a circular fashion, and it's moving at a constant velocity or constant speed. So as a result, based on the definition that kinematics gives us, this is going to be considered uniform circular motion. But here's some key points that students oftentimes get kind of lost on when we're talking about uniform circular motion. So first off, because it's defined as having a constant speed, what that means is that the magnitude of the velocity, the numerical value of that velocity, is going to remain constant. But the direction at which that velocity component or vector is pointing is going to be continuously changing. Okay? And that's a key thing, because if we look back at the kinematic definition of acceleration, acceleration is defined as the rate and change of velocity, which means even though the magnitude isn't changing, because the direction is changing, we still have an acceleration. So you can see it there, what I've got up there. Defined as the rate of change in velocity, a change in the direction constitutes an acceleration. So if we're going to have acceleration in circular motion, it doesn't necessarily mean that we've got a change in the magnitude of the velocity. It's simply talking about an acceleration that changes the direction in which that velocity vector is pointing. So what this means is that an object revolving in a circle is continuously accelerating even when that magnitude or the numerical value of the speed or velocity remains constant. So now the question becomes, well, how do we find the acceleration for circular motion? Well, we go back to this, the kinematic equation for acceleration. This is our starting point. And based on kinematics, acceleration always equals the final velocity minus initial velocity, or v2 minus v1. You can also see this simply as v minus v naught. But in this one, v2 minus v1 divided by a change in time. Well, anytime you have final minus initial, or 2 minus velocity 2 minus velocity 1, whatever, it's a change in that velocity. So in other words, delta v divided by delta t. Where for circular motion, that change in velocity, delta v, that is over an extremely short interval of time. So we take this kinematic idea that acceleration is a change in velocity over a change in time, and now we apply this to the circular motion. So in this diagram, I've got, again, this idea of the stopper on the string, and as it moves through its circular motion and it gets to point A, what we've got is its velocity vector pointing, in essence, parallel to the floor. That's point A, its velocity vector pointing this direction. As it moves the next little increment, and now I've moved at some angle, it's pointing slightly downwards. And what we can do is we can take these two velocity components, the velocity component at A, the velocity component at B, and we can construct a vector diagram where what I've got is velocity A, velocity B, and if we take that velocity A, velocity B, and we make their vector sum, this would be the change in velocity. What we notice is that vector sum, change in velocity, is pointing inwards towards the center of that circular motion. And that's what this triangle right here is showing you. So why is that important? Well, what we know from kinematics is that acceleration always points in the same direction as the change in velocity. So because the change in velocity, that delta V, points towards the center of the circle, acceleration is also going to point towards the center of the circle. And that acceleration towards the center of the circle, that is centripetal acceleration. We also can hear this referred to as radial acceleration. It's symbolized as A sub r, since it's directed along the radius towards the center of the circle. So radial acceleration, acceleration along the radius, or centripetal acceleration. And when it is done as centripetal acceleration or referred to as centripetal acceleration, we typically symbolize it as A sub c. But for the purpose of this video, I'm going to go on and use A sub r. But you can see it both ways. So now we've got kind of an idea of where acceleration centripetal comes in. How do we calculate it? Well, to calculate centripetal acceleration, we use this equation. A sub r equals v squared per r. And what we get is this summation that says, all right, so if you've got an object moving in a circle of radius r with a constant speed v, it's going to have an acceleration whose direction is towards the center of the circle and whose magnitude is a sub r equals v squared per r. By the way, this is why a lot of times we use a sub c, so that that capital R and the lowercase r, even though they're both meaning in essence radius, sometimes we'll have individuals or students that put a capital R in the equation, and that's not what you need to have. So me personally, I like a sub c, but because I'm seeing more and more textbooks starting to use a sub r, that's what I've gone with in this video. Okay? If you're using older textbooks, which let's be honest, most schools are using older textbooks because they don't have money to buy new ones, but that's beside the point. You're going to see a sub c. But newer textbooks, if your school can afford those, or you're in college and you've got the newest textbooks, you're most likely going to see a sub r. But anyway, onward we go. So here's the key point when we're dealing with this equation, because it looks simple enough, but there's actually a lot of information tied up into it. First off is that acceleration depends on velocity and radius. And if you've seen my previous videos where I've talked about equalities and proportionalities, that's what I'm about to do here. We've got this equality that says acceleration radial equals v squared per r. But from that, I can draw two proportionalities. First one is that radial acceleration would be proportional to v squared. The second relationship that I can get is that acceleration radial would be proportional to 1 over r. So here's what this means. The greater the velocity that that object is moving in that circular motion, the faster that velocity changes directions. But it's not just a one-to-one relationship. Take a look at that proportion. A sub r proportional to v squared, which means this. If I double the velocity of that object, 2 squared means that the acceleration, centripetal or radial acceleration, goes up by a factor of 4. That means that the velocity changes direction 4 times faster than what it did before. Again, remember, from kinematics, acceleration is the rate of change in velocity. So if my velocity is doubled, then I'm squaring that, and my acceleration is quadrupled. So the rate of change in the velocity for that object goes up by that factor of 4. Conversely, if I half that velocity, then the acceleration is cut down to 1/4 of what it had been, because 0.5 squared is 0.25. So I end up getting a fourth of the rate of change that I initially had. Conversely, if I look at the second proportion there, radial acceleration proportional to 1 over radius. If I double the radius, then I'm going to half that acceleration. If I half the radius, sorry, I just said that. If I double the radius, I'm going to half the acceleration. If I half the radius, I'm going to end up doing the opposite to that acceleration. So we've got those relationships between velocity and radius and the acceleration. So again, that last little point, the larger the radius, the less rapidly that velocity changes direction, because it's an inverse relationship. Okay. Another key point, and this is a big one, the acceleration vector always points towards the center of the circle, but the velocity vector always points in the direction of motion, which means this. If I go back out to a large screen, as this is moving, again, the inertia of this object wants to carry it off in a straight line. If I've got this in circular motion and I let go of the string, we're not going to see, if it's brought around to this point when I let go of the string, I'm not going to see it suddenly just fly off straight up into the air. I'm also not going to see it continue to move in circular motion directly in front of me. Thirdly, what I'm not going to see is as it moves and I let go, it's not going to move in a curved fashion. Instead, what I'm going to see is it's going to follow its vector for velocity. So if that velocity vector is always a straight line and I let go of it right here, I'm going to see this ejected off in a straight line from the point where it had been, or tangential to the circular motion. Well, as we said, centripetal acceleration or acceleration radial acceleration always points along the radius. So even though the velocity component at the top of that arc is towards my board, what I would have is the acceleration component directly down this string. So one of the things that you can do is make an L with your pointer finger and your thumb and line it up. So at the top of that arc, that circular path, I've got my direction that velocity is pointed, and I've got the direction that my acceleration is pointed. So anywhere along that circular path, I know which direction the velocity is trying to carry it, and I know the direction along which acceleration is acting. Okay? So just a little helpful hint to you on how to figure out which way those two vectors are pointing. Okay? So again, acceleration vector always towards the center, velocity always points in the direction of the motion. And hopefully what you saw in that little demonstration, because I can do the L, what this means is that the velocity and acceleration vectors are always going to be perpendicular at every single point along the path for that uniform circular motion. And the big thing about this is that it shows that acceleration and velocity are not always going to be in the same direction. Right? In projectile motion, if you've watched that video, we launch something along an arc, along a projectile path. And even though I've got a velocity that's in the y component and the x component as it's moving along that projectile path, acceleration due to gravity is always pointed downwards. So in projectile motion, we've already seen this idea that velocity and acceleration do not always have to be in the same direction. Now, when we get to circular motion, we find that velocity and acceleration are always going to be perpendicular to each other. So again, we've got to get out of this mindset that velocity and acceleration are always in the same direction. And I know some of you are thinking, wait a minute, earlier in the video, he said that delta V and acceleration always point in the same direction. Yeah, they do, because that is the change in velocity. It's the vector sum of the two individual velocities. So the individual velocities and acceleration do not have to be in the same direction, but the vector sum or change in velocity and acceleration are always in the same direction. So please don't get those things mixed up. Okay? There is a difference between the individual components of velocity and the vector sum or change in those velocities and the way that they have a relationship with acceleration. Okay? So 3 additional concepts to go along with this before I finish out this video. The first is that of frequency, and this is the number of revolutions per second. And the way that we typically go about finding this is we put something into circular motion, and we've got a stopwatch. And what we'll do is we will count how many times the stopper or whatever the object is makes one complete revolution over the time period of 10 seconds. Okay, so I would start my timer and say, all right, 1, 2, 3, 4, and count up, say 10 revolutions, stop the timer, and see how long it took to take those 10 revolutions. Then I can divide. So, for instance, if I got 5 revolutions in a time period of 10 seconds, then I would have 5 divided by 10, or half a revolution per second. Okay? So that would be my frequency. Conversely, we have this thing called period, and it's symbolized by a capital T, frequency by a lowercase f. In wavelengths, we do frequency in terms of nu, which is kind of a fancy V, but that's a later video. But period, or T, this is a time required for one complete revolution, and we find that it's equal to 1 over frequency. So in the previous example, if my frequency is 1/2, then my period would be 2. In other words, it would take 2 seconds to complete 1 revolution. The last idea that goes along with this is that for an object revolving in a circle at constant speed, that speed is going to equal 2 pi r divided by the period, because in 1 revolution, that object is traveling 1 circumference. And hopefully you learned from math that circumference has a formula of 2 pi r. So the velocity is the circumference of that circular motion divided by how long it takes to go through that 1 circumference. So that is circular motion or uniform circular motion with regards to centripetal acceleration. Hopefully everything made sense. If not, feel free to leave questions in the comments and I'll get back to you as soon as possible. Also, if you've got ideas for a future video, leave those in the comments as well. And don't forget to subscribe to this channel. That way, when I post new videos, you can get notified of those videos and come back, watch them, and hopefully learn something. So thanks, and take care.